conference will now be recorded.
All right, everybody. So today we're going to do a lesson on quadratic regressions. If you go back in time, you'll remember linear regressions. So we did linear regressions, right? And then we did exponential regressions. And this is going to be the last one we're going to be dealing with, quadratic regressions, all right? And what you're going to notice in mathematics is quadratics tend to be the model that you use for lots of different things. The biggest one being when you throw something in the air, it comes back down, and that's looking like a quadratic, right? So quadratics happen a lot because problems in the real world deal with gravity a lot, right? So when things go up, they come back down and they look like a quadratic, and so they're modeled by quadratics. So just keep that in mind as you go. The big thing you need to know is you first have to have some points, right? And so if you go menu, and you can do this on an Inspire, or you can do this on Desmos, and I'll show you in a little bit. So 6, 1, 6. Open up a set, and I'm just going to make up a group of numbers. 1, 2, 3, and 4. And I did not type it inside. 1. See what it's doing? That's so weird. 1. What a troll. 1, 2, 3, and 4. Open up a set. 1, 1, 2. Let's see, plus 1 plus 3 is 5, and plus 5 is 10. So let's say the points are 1, 1, 2, 2, 3, 5, and 4, 10. Press OK, and it will give you the line of best fit, right? Or the quadratic of best fit, right? And we don't have an R value here. We have an R squared value. Now listen, if you're taking like a STAR test or an EOC, they don't really care about the R squared value. But the closer it is to 1 or -1 for R squared when it's quadratic, the closer it is to a perfect fit, yeah? So I picked one that was a perfect fit. So what is this saying? This is saying if the equation is in the form of ax squared plus bx plus c, it would be 1x squared minus 2x plus 1, or plus 2, sorry, plus 2, right? So it's real simple. If you've done linears and you've done exponentials, this is not going to be hard, all right? All right, so let's do a couple examples. Suppose you're standing on an observation deck at the top of a tower and you drop a penny and watch it fall to the ground. The table on the right shows the penny's distance from the ground after various periods of time in seconds, all right? All right, so the independent. Remember, like we said a million times, independent is almost always time, right? So time, and dependent would be distance in feet, right? From the ground, really, right? And why are the distances going down? Because the penny's being dropped and it's getting closer and closer to the ground, yeah? All right, so the equation. How do we get the equation? Well, real simple. We're going to doc B first, right? We're going to do menu 616, open up a set. All right, we're going to type in those numbers, right? 0, 2, 4, 6, 8, 10, right? 0, 2, 4, 6, 8, 10. So 0, 2, 4, 6, 8, and 10. Open up a set. Did not hit a set. Open up a set. This program is really buggy here, so I apologize. All right, open up a set, and we're going to put those values in. What do we got? We got 1821, 750, 1757, 656, 1245. All right, let me write those in real quick. All right, so we got 1821, comma, 1757, 1565, and what are my other ones? We got 797 and 221, 797 and 221. All right, go down, press OK. All right, so this is interesting because I just got a mismatch error. So if you've ever seen this mismatch error, it means I have what? 1, 2, 3, 4, 5, 6 values there. And what do I have here? 1, 2, 3, 1, 2, 3, 4, 5 values. So that's a dimensional mismatch. So I have to fix that, right? I got to figure out where my mistake is. So I'm going to have to go back over here. Usually when this happens, it's best to just start over again. 1821, 757, 656. I missed this one. So 1254 or 1245, I believe, comma, and then I got the other ones. All right, there we go. All right. Hey, this is interesting. When you see negative 16x squared, that's usually being modeled by gravity. So if you ever see a quadratic that has negative 16x squared, you're usually dealing with gravity in that case. So that you'll see that a lot. So there's our equation, right? Negative 16x squared plus 0x plus 1821, right? So that's what we would write, right? Negative y equals negative 16x squared plus, and what do we have? We had plus 1821, right? All right. So there's our equation. And that's not going to be an r value. That's going to be an r squared value, right? And our r squared value, I think, is perfect if I'm not mistaken. Yeah. So the r squared is 1 here. Remember, for linears and exponentials, the r value is it's just the r value, not the r squared value, right? The correlation coefficient. So it's 1 here, so that's a perfect fit, right? All right, so r squared is 1, and it is strong. In fact, it's very strong. All right, we're not going to worry about the domain and range. I'm going to take that out of this lesson, okay? So you can ignore that. The y-intercept was 1821, which means at the point 0, 1821, that's where you drop the penny from, right? 1821 is what you drop the penny from, right? And we're not going to deal with the zeros, so you can ignore that. Over the years, I've been changing this because it's really not what this lesson's about, okay? And then we're going to answer 2 questions. Where would the penny be after 12 seconds and where would it be after 15 seconds, right? So to do those 2 times, what you're going to do is you're just going to type them in, right? So you're going to do negative 16 times, remember what we think x is going to be 12 seconds, right? So we're going to do 12 squared plus 1821, right? What do we get? Okay, this is interesting. After 12 seconds, it's at negative 483 feet. You're like, well, how the heck can that happen, right? Well, so right around time 11, it's probably going to hit the ground, right? All right. So if we want to say 12 is whatever it is, what did we say it was? Negative 483. You're like, well, how the heck can that happen? Well, if that's the ground, then it would hit the ground after 12 seconds. It would already be stopped. But if you say you dropped it to the ground and then there's a hole in the ground, it could keep going down, right? Which is kind of a dumb question. I kind of wish this was an earlier time. I wish it was 9 seconds, we'll say. But if it goes negative, really think about that, because hopefully, you just made up a weird problem that doesn't really work. Let's change this problem to like 9 seconds, right? And then let's say, oh, I don't know, 5 seconds, right? We'll do these 2. 9 seconds and 5 seconds, right? All right, so let's redo this with 9 seconds and 5 seconds. So the easiest way to do this is just come up here, paste that, change the 12 to a 9, and you're done, right? So after 9 seconds, about 525 feet, right? So after 9 seconds, about 525 feet. And then after 5 seconds, let's see, just change it again, right? Change it to 5. And after 5 seconds, about 1421, right? And after 5 seconds, about 1420. Okay. All right. That's really all there is to that. All right. So one more problem. On the table to the right lists the number of Americans who are expected to be over 100 years old for the selected years. Oh, kind of a sad story, because I'm videotaping this. I'm recording this in El Paso right now because we are in El Paso because we were just a couple weeks ago, we were celebrating my wife's grandmother's 100th birthday. So shout out to Grandma for this. She was one of the people to be on this list. So first thing we notice, these are not 50 people, these are 50,000 people. So when you type these, you're going to have to put it in as 50,000 and not 50. If you do type it in as 50, just understand that the y value is going to be times 1,000. And I'm actually going to do it that way. No, I'm not. I'm going to put it in. I'm going to put it in as thousands. So 50,000, 56,000, yada yada yada. Okay. The independent is, now be careful. This is number of years since 1994, right? And the dependent would be the number of 100-year-olds in the US, right? Okay. So that means 1994 would be 0. This would be 2, 4, 6, 8, and 10, right? All right, so I'm going to start this over again. Ready? Block B, we're going to start over. Menu 616, menu 616. Open up a set. All right, 0, 2, 4, 6. I think I went to 8. Let me make sure. I went to 10, actually. So one more. Comma 10. Go down, open up a set again. All right, and remember these are 50,000. These are thousands. So 50, 56, 65, 50,000, 56,000, and then what was my next one? 65 and 75. And our last one was 110,000, right? All right, press OK. Good Lord, did it again. Where's the mistake? 0, 2, 4, 6, 8, and 10. Got another dimensional error, right? So I should have 6 of these, right? 1, 2, 3, 4. Oh, wow. What am I missing? Let's see which ones I'm missing. I'm missing 50, 56, 65. 50, 50, 56, 65. Yeah, I feel like there's one at before that. 65, 75, 94. Why do I feel like I didn't do 94? Yep, that's it. I missed the 94. I'm not sure how I did that. 94,000. And there we go. All right, so if you ever get a dimensional error, that's why, right? Now, these are not going to be pretty, right? But what are we saying? It's about 401x squared, right? Plus 2039. So y equals 409x squared, right? Plus 2039x plus what? Plus about 5,000 or 50,071, right? 50,071. Yeah. Let's look at the r squared. Fix that. It should say r squared. The r squared value is about 0.997, which is fantastic, right? 0.997, very strong. Yeah. We're not going to do the domain. We are going to do the range. The range is around 50,071, right? The zeros we're not going to do tonight. And then predict the number of 100-year-olds in 2018, or sorry, 2018 and 2051. Okay, so we're going to have to do 2018. So we're going to have to do to find the year, we're going to have to do 2018 minus 1994, right? So what are we at? 4, 9, 10, 11 is 2. That's 0. Oh, that's 24 years. So that's 24 years. And then 50, right? Let's see, 2050 in 1994, 6, 4, 14, 5, I believe. 56 years, I believe. 56, yeah? All right, so let's do 24 years and let's do 56 years. Wow, that is too small. All right, so we're going to do the equation. What are we doing? We're doing 401 times, what did we say x was? We said x was 24, right? So 24 squared plus 2039 times 24 plus 5,007, right? Press enter. About, what are we looking at? About 284,919. 284,919. 100-year-olds, right? 100-year-olds. All right. And what about 56 years? You can do the same thing. Remember, if you have an Inspire, you can just go up there and highlight that and then just change the numbers to 56, right? Change that to 56 and change the 24 to 56. And we got what? About 1.37 million, right? 1376. 1376. So that's 1,376,000. What are we looking at? 727. 727 100-year-olds, right? And that kind of makes sense, right? As time has gone on, medicine's gotten better and people are living longer. So, all right, that's really all you're doing, right? You're just doing quadratic regressions. And I was going to show you, if you needed to, you can also do this on Desmos. So if you do Desmos, let me show you this. If you type in Desmos quadratic regression, you can go in there, you can change these values, and it'll give you the line of best fit for a quadratic regression. It's the same stuff, right? Just go in there and change those values, and it'll give you the quadratic. All right, so not a big deal. Same process as if you had an Inspire. But that's really all there is to this lesson. So hope that makes sense to you. Take care.